Hello, this is Dr. Lori. Welcome to my probability friends. I'm going to review some of the primary concepts around probability by showing some examples of questions that can be answered by probability. So one of the first kinds of questions is about a coin toss, and we use this example a lot just because people can relate to tossing a coin. And when the question asks something like a fair coin is tossed 5 times, what is the probability of achieving at least one? And you could put in there either heads or tails. In this example, we'll use at least one heads. What that means is, and I'm going to jump down to this space down here at the bottom, that means that at least one heads is you could get 1 heads, or 2 heads, or 3 heads, or 4 heads, or 5 heads. The only possible choice that you would not get at least 1 heads would be as if you got 0 heads. And so let's start thinking about this by actually looking at our little coin. So here's our coin. And then we take it and we toss it, and our toss can either become a tails or a heads. Now the reason that I've drawn the branching diagram the way I have is because of this top line right here. What I'm really interested in calculating is the time that I've thrown all of the throws to be tails, because what I know about probability is that the whole entire space has to add up to 100%. And if I can calculate just one thing, and I don't have to calculate all of the other things, then I can just do this question by subtraction. So I want to show you the answer visually in a couple of different ways. So first of all, I take my coin, I toss it. I'm either going to get a tails or a heads, and my chances of each one are 0.5. So I have 0.5 there and 0.5 here. And once I've gotten this heads right here, this one, then I have achieved at least 1 heads. Anything that I do branching after that, whether I get tails or heads, doesn't matter, because I have already achieved 1 heads, and that will be part of my I've achieved at least 1 heads answer. It's only in the case that I achieve tails and continue to achieve tails throughout the experiment that I did not meet this particular outcome. So let's go ahead and follow this on out. So let's say we had another toss. We started here and we tossed, and we either got tails or heads again. And the chances there are 0.5 and 0.5. And the thing that you'll find is that if I take this probability and multiply it by this next one, I actually get the probability of getting the tails twice. So if this first toss I got tails, that's half the time. And then of that half the time I tossed again and got tails, again that's half of half. Half of this half. So this ends up being 25%. And if I continue this on out and I toss again, and my chances of each of these outcomes are 0.5, the next time is 0.5, and then finally I get to the end and it's 0.5 again. What I end up with is half of half of half of half of half. And so conceptually, the only way to get tails 5 times in a row is equal to 0.5 taken to the 5th, or 0.5 times 0.5 times 0.5 times 0.5 times 0.5. The answer to that question is 0.03125. See if I can write it big enough right there. I want you to also think about this conceptually, like let's do this as sort of an applied example. Let's say that I toss the coin 100 times. Well, after my first toss, half of them will have been tails. The other half will have been heads, and so on. And this one I would continue to toss as well, and these continue to branch, and so on and so forth. But it doesn't really matter because all of these have met this criteria of at least 1 heads. After I toss these 50 coins that ended up being tails, I end up with 25 coins that were tails both times. And I continue on. Half of 25 is 12.5. Half of 12.5 is 6.25, and half of 6.25 is 3.125 out of the 100 that I started with, and that's the same number that we get here is 0.03, or 3 out of 100, 3.125 out of 100 times. I would have gotten tails 5 times in a row. How many of you ever have thrown a coin and you're like, wow, you have to throw it 5 times in a row, an awful lot, in order to actually have that happen to you. It's pretty uncommon. So the third way that I'd like to show you is by actually doing the calculation using the binomial coefficient, also called the choose coefficient. In other words, this coefficient right here tells us how many ways you can choose x items, here's our x, out of n tries. And in this particular example, x is equal to heads. We already know it was tossed 5 times, so n is equal to 5. We could write the n is equal to 5 up here, n is equal to 5, and then tails is equal to n minus x. I actually reversed the color, sorry if that's confusing. So here we have x, and in this first row, I didn't get heads at all. And so the way we calculate that, we could actually calculate out this choose coefficient for all of these situations. That's beyond what we're covering in this video. But the choose coefficient for this first row, where x is equal to 0 and n minus x is equal to 5, the chances, or the ways to possibly do that, there's only one. Here we have 5, 10, 10, 5, and 1. And this is symmetrical because of our fair coin, which is a probability is equal to 0.5. It's equal to half. And if you think about it, really, we just proved that there's only one way of doing this where we have 5 tails in a row. You have to get a tails first, and then a tails second, and then a tails third, and then a tails fourth, and then a tails fifth. That's the only possible pathway that you can get 5 tails. Anything, this would be 0.5 taken to the, and here's our number, taken to the 0. Anything to the 0 is equal to 1. And so this reduces to 1. And here's the other probability, 0.5, or q, taken to the n minus x, which is equal to 5, so 0.5 to the 5th, and that's exactly what we got here. And so that is equal to 0.03125. Now, neither time did we actually come up with the answer to this question. This question asks what's the probability of at least 1 heads, and so we would have to take, in order to find this space down here, the other possible choices, we would need to take 1 minus 0.03125. And you can do that on your calculator pretty easily. It's close to, but not exactly. It's close to 97% of the time. And if we were theoretically to add up all of these possible times, and we actually showed all the branching and continuing to branch out and all that kind of stuff, like each one of these is going to branch and so forth, because we tossed them all. If we added all of those up, we would get the inverse of 3. In other words, all of the 100, if 3.125 were tails, 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 the other 97-ish, 96 point whatever, would actually fall in this other space where we achieved at least one of the heads. So that was kind of a long description of how to get to the answer for that particular question. This next question is very similar, where we have the probability of an event, except that we've changed the probability so that it's not a 50-50 thing that's happening. The rest of this question really is essentially the same. And so the probability of an event might be that somebody has an opportunity to go rock climbing this weekend, or somebody is selected for a certain thing, or you have a dice that has 10 sides and you roll that dice, or you have a multiple choice question that has 10 possible answers. So there are a bunch of different scenarios that could apply to the probability of an event being 0.1. So in this case, we just need to change what we apply to each of these. So here's our event occurring. This is 0.1, or 10% of the time. The other arm then would be the alternate, or 90% of the time there would be no event. Let's say this is the first time you roll that dice that has 10 sides. Here's the second time you roll that dice, the third time, the fourth time, and the fifth time. And so each of these times, we didn't roll that particular event number. That will happen 90% of the time, and only 10% of the time will the event occur. Again, this thing here would branch, and then that would branch, and so forth. So these continue branching. We're just showing the path of the probability that's the opposite of having at least one event. In other words, the probability of the event never occurring. So here we would have 0.9 again, 0.9, and 0.9. And just as we found before, if we take that 0.9 taken to the number of chances, and again here we have our 5 chances, so n equals 5, taken to the 5th power, what we end up with is 0.59049. I need to scoot over a little bit more. 0.59049. So the chances of never having 0 events then is the opposite of the chances of having 1 or more events. So again, here we have our space that would achieve what the question is asking, but we just calculated something else. We calculated the inverse of that. We calculated the event not occurring 5 times in a row. Again, we could also calculate this same number by remembering that we could just calculate out all of these numbers. Here we have one possible way of achieving no event 5 times in a row, 5 ways of achieving 1 event and 4 no events, and so forth. We can fill this in. And technically, you could, oops, this is a 5. So technically, you could calculate each one of these probabilities right here and add them up, or you could calculate this probability on this row and subtract it from 1. And so that's the simpler. The inverse of at least 1 event is 0 events, and so the probability here of the event is 0.1 taken to the where x is equal to 0, and this is 0.9 taken to the n minus x. In other words, 5 minus 0 is 5. And so we end up with the exact same calculation that we did over here that's, sorry, off the page, just a tiny bit, 0.59049. Now, as a reminder, that does not answer the question that they asked up here. So now that our probability of event and not event are different from each other, it's really, really important to keep track of which thing they're asking about. Because 0.9 to the 5 is very different than 0.1 to the 5, and we end up with a very different number. Also, here we have 0.59049. What they're really asking is how much is this quantity down here. And we haven't calculated all of those out. So what we need to do is take 1 minus 0.59049, depending how much they want you to round, would come up with our answer. And so that ends up being, so we'll just say equals 0.40951. So the answer to this question is different than the answer to this question. So there's our answer. The third question, that is kind of a common way of asking something about probability, talks about uniform distributions. And so in a uniform distribution, depending on kind of what they consider to be the lower number and the higher number, let's say that we have a uniform distribution that ranges between 10 and 30. Basically, what that looks like is it is the same all the way across. And so we don't have a bell-shaped curve, we don't have a chi-square curve, we don't have something that looks higher in the middle and lower on the sides. It's just uniform. The chance of getting something over here is the same as the chance of getting something over here or in the middle. The probabilities are all the same. And so often a question like this will ask you, it'll say, given that the uniform distribution is between a certain range, so let's say here 10 and 30, so this difference right here is 20. 30 minus 10 is 20. What's the probability, let's see if we can pick a new color, what's the probability of getting some number between 18 and 23? And so what we're asking specifically is about a smaller range. And so 18.1 would count as being included, 17.9 would not count as being included in that particular probability. So the difference between 18 and 23 is 5. What we end up with then is the probability of choosing something between 18 and 23 is 5 divided by 20, or 20, can I write 25% of 25% of the time. I just want to do that over. Let's get a better pen. So 0.25 is equal to 25% of the time I will choose a number that falls in this range right there. So the probability is equal to 0.25. The final kind of question that you might be asked about probabilities is, can you calculate an expected value and a variance or a standard deviation given a set of parameters? And so a lot of times we'll say, okay, maybe I have however many tries I have commonly. We might think about a multiple choice test. Let's say I give a test and I have 80 questions on my multiple choice test. And if I offer 4 possible answers, if somebody like A, B, C, D, if somebody were to randomly select A, B, C, or D, and it truly was just random, the probability of getting any one question right is 0.25. Inversely then, the chances of getting it wrong are 0.75. So now we've defined our question. Our expected number of correct would simply be equal to the number of questions I have times the chances of getting each one of them correct. So that would be equal to 80 times 0.25, which is equal to 20 questions I would get right. So if there are 4 possible answers, I have 80 questions, I'm going to get probably somewhere around 20 of them correct just by guessing, not by knowing the material at all. Now I can also calculate a variance and or a standard deviation around that by this equation right here. So my variance is equal to 80 times 0.25, also times 0.75, and that number actually comes out to be equal to 15. Now variance, a lot of times people struggle with the concept of variance, so we want to convert that to standard deviation. Standard deviation has the same units as our mean, and so that's very handy. Variance doesn't help us as much in that particular area, but we need to take that same number we just calculated and take the square root of that, because variance is simply standard deviation squared. So I'm going to take the square root of 15, which is equal to 3.873. So my expected value, or the number I would expect to get, is somewhere around 20. The standard deviation gives us an estimate of how spread out that would be. If it was a 95% confidence interval, for example, it would be 1.96 times 3.873. And so this, the mean and standard deviation that I would expect to get if this was truly just sort of randomly chosen answers would be a pretty low score on a multiple choice test. So you don't want to just be guessing. So that concludes our discussion about some of the common probability type questions.